Thanks, everybody. I think we can start. Thanks, everybody, for being here at the Physics Department Colloquium today. I'm very pleased that we have today Cristian Peña, one of our alumni from Caltech, a PhD from 2017, who has moved on to be a Lederman Fellow and develop a very ambitious program at Fermilab for CMS at the LHC and be part of the quantized DOE-HEP effort for quantum sensing in the base program with a lot of exciting developments, instrumentation, and physics. Cristian did his undergraduate work at Universidad Técnica Federico Santa Maria Valparaíso in Chile. And I can say that because I know a little bit of Spanish, but also I was there as a reviewer of their institute. And I have got to meet a lot of the people who are engineers and also experts in theoretical physics, amazingly enough. So coming back to Fermi era with experimentalists, engineers, and theoretical physicists working together. It is very exciting to present Cristian Peña. And I want to just mention that just a few days ago, he got awarded for one of these precision instrumentation enabled physics program that we have at the LHC. He got awarded the Junior Physicist Award for this particular device and detector that he will present to us today. So with that, I give it to Cristian.
Thank you, Maria, for the kind introduction and for the invitation to give the colloquium today. I'm really honored for that. As you said, Caltech is my alma mater, and I'm happy to have the opportunity to talk to you today about precision instrumentation at the LHC and quantum information science enabled discovery for high energy physics. So right off the bat, I want to acknowledge the people that I am collaborating for the research that you will hear about today. And that includes the Fermilab Large Hadron Collider Physics Center, or LPC, the LPC LLP team, which I helped form, and where we're pursuing cutting edge searches for long-lived particles at the LHC in CMS. Also on the instrumentation side, the Fermilab Cms Timing Detector group, which is one of part of the things that I've been doing for which I was awarded, what Maria mentioned. And the last but not least 2 points is that I've been keeping my ties with Caltech in collaboration, and this is allowed by the Caltech CMS Detectors and Physics group, which we're still pursuing very ambitious program at the LHC. And more recently, I have also been part of the Caltech InQNet group, which includes JPL, Fermilab, from where I'm from, Harvard and Calgary in the collaboration, and where we're pursuing quantum information science enabled experiments, including teleportation, and more recently, exploration of dark matter. So the particle physics aims to answer fundamental questions that will shape our understanding of the universe. And these questions are the grand challenges that we need to face in high energy physics and cosmology today. And among the grand challenges, we find what's the nature of dark matter, the precise determination of the Higgs boson properties, and the detailed understanding of the neutrino physics, as well as a few others. But today I want to focus on the first two, because that's what I've been doing for the last about 8 years in my research. So now to tackle these grand challenges, as I call them, we must explore nature at the frontier of detection technology. And that's because throughout history, transformative discoveries come often hand in hand with technological breakthroughs. One great example of this was when in 1965, when a precision instrument enabled a transformative discovery. As I said, in 1965, Penzias and Wilson, using a microwave horn antenna, unexpectedly discovered a new signature that was consistent with the cosmic microwave background. Their discovery reshaped our understanding of the world by giving us hints about the Big Bang theory, and also transform the field of cosmology. Today, I'm gonna give you 2 ways in which I am addressing these grand challenges by doing something similar, which is being at the frontier of detection technology. The first one is exploring nature at the smallest length scales. at the Large Hadron Collider. And we do that by smashing protons together at nearly the speed of light and studying the debris that come out of the collision. Now, if you transform the collision energy to a length scale, then we realize that we are proving length scales that are 1e minus 16 centimeters, which is the same as 10,000 times smaller than the proton size. So very, very precise. And one important transformative discovery that we had at the Large Hadron Collider was the discovery of the Higgs boson in 2012. The Higgs boson is the only fundamental particle that we have ever observed which carries a spin 0. And it's also responsible for the masses of all fundamental particles, including itself. It took us nearly 50 years since the discovery, since this prediction by Peter Higgs and others, to its discovery by the CMS and Atlas collaboration. And it was truly a remarkable scientific achievement, and one made only possible by advancements in accelerator technology and detection technology. And one in which Caltech actually played a crucial role since the beginning, with Barry Barish making the first ever Higgs to gamma gamma plot that we've seen, and more recently with the first observation and evidence that the Higgs is now decaying to a pair of muons, in which again the Caltech group play a crucial role. The second way in which I am addressing the grand challenges is by using quantum sensors to probe fundamental physics. Recently, quantum sensors have emerged as a paradigm shift in technology, and they are enabling quantum computers, quantum communications, and as I said, more recently, fundamental physics. In particular, what we are doing is using quantum sensors to probe dark matter. And we're probing dark matter with these quantum sensors in the unexplored low mass regime. In this picture, we have a superconducting nanowire single photon detector, which is a type of quantum sensor. And we call these SNSPDs for short. And they have been proven to have an energy threshold that is about 100 milli-electron volts, which is about 10 times better than the current state-of-the-art dark matter experiments. And if you transform that using the kinetic energy that a particular mass of dark matter, we can obtain that we are probing dark matter masses with these energy thresholds of about 100 kilo electron volts, which is 1/5 of the mass of the electron. And I want to point out that this is a new emerging research field and one that has been fully supported by the US Cosmic Vision report that was released in 2017. Okay, so now going into the first topic of the talk today, I want to discuss the science and technology of the compact muon solenoid experiment, or CMS, at the Large Hadron Collider. The compact muon solenoid experiments is where I've been doing my research for the last 8 years. And now let me refresh your mind about the Large Hadron Collider. So it's a 27-kilometer ring particle accelerator, and where we collide protons are nearly the speed of light every 25 nanoseconds. And we take that velocity and we usually convert that into energy, and therefore we achieve the energy of 13 tera electron volts, and which makes the LHC the most powerful particle collider in the world. Okay, so there is a rich physics research program at the Large Hadron Collider, but I want to highlight one very important process that we have yet to observe. Being the only spin 0 particle, the Higgs is the only particle or only fundamental particle in the standard model that can undergo a 3-way interaction with itself. This is represented by the diagram here in the middle, where you see these 3 dashed lines, each one representing a Higgs boson, meeting at a single point. Now, measuring the Higgs self-interaction is crucial in determining the shape of the potential, which ultimately will determine the fate and stability of the universe that we live in. And therefore, this particular measurement is the flagship scientific goal that we have at the next phase of the Large Hadron Collider. Now, measuring the Higgs self-interaction is a major challenge in itself, okay? And that's because in order to measure the self-interaction, which is this diagram here in the left, we need to produce 2 Higgses. And now producing 2 Higgs boson is about 1,000 times more rare than producing a single Higgs. And that's partly because the self-interaction is very feeble, very, very small. And partly because the diagram in the left and the diagram in the right, they experience a quantum mechanically interference and making the process smaller. In order to then see this fundamental process, we just need many more collisions. So now, in order to get this increase in the rate that we're expecting, what we're doing or what we need to do is to increase the focusing of the beams at the interaction point. And in order to do that, what we do is that we need to make new magnets that are able to withstand 50% more increase in the magnetic field. And that's very challenging because in order to produce these magnets in large scale, that usually takes about 10 years. But we're very excited to see the progress. And this is actually a picture of a functioning magnet coming from Fermilab that's able to produce the required magnetic field using this new technology called niobium-13. So based on these encouraging results, we're very excited to start operations in 2027. Now, the increase in the luminosity, which comes from these beams being more focused, will pose a major challenge for the reconstruction of particles in the detector, in CMS. And that comes from the fact that by focusing the beams into a tiny spot, we're increasing the probability of having a very energetic collision, which is the one that we're looking for. Let's say that's the one here in the middle. But at the same time, we're increasing the probability to produce other soft collisions, which are polluting particles for our detector. The only thing that they do is they confuse our reconstruction algorithms and they confuse the way that we see the event. But we want them because we need to achieve this luminosity. And we call this effect, this polluting effect, we call it pileup. And perhaps as me, you're also familiar with a different type of pileup in sports. I'm a big football fan. And the questions that I usually ask when I'm watching football on Sundays is it's where the ball is at, maybe perhaps with a different language when I'm actually watching the game. But when I'm working on CMS, the questions that I ask are usually different, but very related, which basically the question that you ask is where are the particles originating from or where are the particles coming from? So in a sense, the pileup challenge is to correctly assign the particles to the vertex from where they originated. So that's the essence of the pileup challenge. And now I want to show you a picture of how that works. So what we do ultimately is we collide the protons and then we reconstruct what happens after the collision. Let's say you have a process that you want to observe, and in this case, for example, the Higgs boson will decay to other particles, and some of these particles will be quarks, and then they hadronize and they produce the jet. So jet is the hadronization of quarks or gluon that happens inside the detector. And we want to reconstruct this jet as precisely as possible. But now having these extra collisions, these polluting collisions, they go in the vicinity of your jet and they smear the quantities that you observe. And if we don't solve this challenge, what will happen is that we will have detrimental effects on the reconstruction, and ultimately we will not achieve the full potential that the LHC can deliver. That's one way to see it. The other way to see it is that we have an opportunity to enhance the capabilities of the CMS detector. And let me explain you why we have this such opportunity. Up to now, we have relied mostly on position reconstruction because we have a very, very detailed tracking system coming from silicon. But we have left off a particular ingredient of the particle space-time reconstruction, which is time. And now, if we were to precisely measure the time coordinate of a particle, then we can use that time, which is an independent handle, to observe where the particle was coming from. Therefore, we have this opportunity now to introduce a new dimension into the CMS reconstruction in the way of timing. Now, this is how it works. In here, we simulate real collision events, which are represented by the red dots, and we reconstruct the vertex using the position only, and those are represented by the vertical yellow lines along the z-axis, which is the horizontal axis. And you can see that what happens is that we start to see degeneracy on the number on the reconstructed vertices when we only use position information. Now, if we were to have timing, what will happen is that we can run a 4D vertexing reconstruction. And by doing that, you can see that the blue dots track the red dots, and therefore we are lifting the degeneracy and we're solving the pileup challenge. Another way to look at it is to slice, that we are slicing the y-axis, which is a time domain, we're taking very precise snapshots. And therefore, we're going from one very blurry picture into a sequence of now clear snapshots, or in other words, a movie which is very clear. So now the natural questions that come next is how precise does the timing measurement need to be? And here's the logic to arrive to the result. So remember, we want to achieve a factor of 10 in the collision rate to measure the processes that we want. Then, therefore, what we really want is to achieve this increase in rate, but having the Peña levels, which means reducing this confusion coming from Peña to the current conditions of the LHC. Therefore, we need about a rejection power of a factor of 10 to get back from where we will be to what we want to be. And another fact is that in the LHC, the typical beam spot is about 10 centimeters in the longitudinal direction, or in C. So therefore, to get this rejection power of 10, we need a resolution in the beam spot of about 1 centimeter. So now if you transform 1 centimeter for particles traveling at the speed of light, that gives you about 30 picosecond precision. And that is actually very challenging, not because you can this can be achieved, but what we need to do at the Large Hadron Collider is take these 30 picoseconds and create millions of channels with this precision. So that's the fundamental challenge. And after this realization, the Caltech and the Fermilab CMS groups have led the way to propose a new project within CMS, which we call the Timing Detector. And it's a sustained effort for R&D to push this detector. And now we have come to the realization of what we need to do. What we will do is we will install 2 new subdetector systems right after the tracking systems, which are all the lines that you see in the picture. And in the central region, which we call the barrel, we will, in blue, we will install a technology which is based on scintillating crystals plus silicon photomultiplier to achieve the 30 picosecond resolution. And in the end cap, which is the forward region in green, we will use a new technology based on silicon sensors with gain in order to withstand the amounts of radiation which are higher in the forward region. So, okay, so let's pause here a bit because now we have come to the realization that we have to have this new collision rate. We have come to the realization that will be a challenge, and we have come with a solution on how to overcome this challenge. But another way to look now of what the timing detector, the new timing detector will give you is look at what we will do for some of the key measurements that we want to do at the next phase of the LHC, or the Large Hadron Collider, the high Lumi version. And as I said before, what we're doing by introducing the time domain is that we're recovering the ability to distinguish these polluting particles, these Peña particles, from particles that you are really interested in. Therefore, the physics objects will be better, and therefore our background rejection to standard model particles will also be superior. And that you can see in the plot on the right, where we're trying to detect new particles in the context of supersymmetry. In this particular example, neutralinos, which are dark matter candidate. And what we do is we extend from the blue curve, which is, this is a 5 sigma discovery rich plot. And we go from the blue curve to the red curve. From the blue curve, which we don't have timing.
Cristian, for me, the slides do not advance. Is this for everyone, or is this only me?
Okay, yes. Okay, so I was saying that we were going from by having this enhanced capability from timing, what we do is we go from the blue reach of discovery of these new particles to the red one. And that's about a 150 GeV increase in this discovery reach. And that's a big deal, even though maybe 150 GeV for you doesn't ring a bell. I can then translate that to you in a different way, which might be more enlightening. It is that when you increase the mass of these particles, the rate at which they happen is much smaller. So basically what we're doing is we're probing now a 3 times more rare process by having timing information. So now, if you probably you've heard that we are doing a great job at excluding supersymmetric particles or parts of the parameter space of supersymmetry. That happens for particles that are prompt, but when these particles fly off in the detector and then decay at some point in the detector, we are not doing so good. And these are newer searches that we are performing. In this case, we're trying to look for now neutralinos again, but the neutralinos are not stable forever, and they actually can decay inside the detector. And because the neutralinos are massive, therefore they travel at speeds that are smaller at the speed of light, and they arrive, or the decay products, moreover, they arrive late at the detector. In this case, the decay product is a photon, and therefore the signature is a delayed photon. And this is something that the Caltech students are actually pursuing very actively, and many have worked on this type of searches. And again, because of the time component of this search, the timing performance that will be enhanced at the high Lumi LHC will reduce the beam spot resolution, or will increase the beam spot resolution by about a factor of 6. And in here, we can see the improvement in this plot. The y-axis is the lifetime, or the decay length of the particle, one parameter of these long-lived models. And the x-axis is the cutoff scale, which is related to the mass of the neutralino. And what you want to do here is to cover as much white space as possible. That tells you that your search is more sensitive. And you can see in green or in red, that's what we will be able to do without this timing upgrade. And in blue, you see what we will gain. It's a very big increase in the reach for these particles. Another way to see this is coming back to the Higgs sector. And in that case, we can quantify the increase in the number of events that we can recover, that because of using timing information by looking at the constituents that make up the Higgs boson. And when you do that by using timing, you see that we recover about a quarter, 25% of the events, which you can interpret as that we will need less data in order to make particular discoveries, or we will discover these things earlier because of having timing. And these kind of plots were a key part of the approval, or to make the timing detector a fully fledged project by the LHCC Commission at CERN, and then more recently ratified by DOE into a full-fledged project in which we can pursue the construction of the timing detector. So that brings me to my next slide. So this is a more detailed picture of what the timing detector will look at CMS. And again, this is a major challenge, because not only we need to produce the sensors that can deliver this time resolution, we need to produce new electronics, new synchronization systems, we need to do cooling these detectors, and they're very massive in terms of surface and number of channels that we need to produce. So in the case of the barrel region, again, that's the central region in green, we use a technology which composes of scintillating crystals, or LYSO, and read out by silicon photomultipliers to read the photons that we're producing by scintillation. And these uses about 40 meter squares of surface, which translated about 350,000 channels. And in the NCAP region, which need to sustain a more harsh environment in terms of radiation, you need, even though we need to cover about 15 square meters only, the number of channels needs to increase to about 4 million. And again, we need to get each single channel synchronized to the precision of 30 picoseconds. That's a major challenge. And then now that you have the challenge, I want to go back in time a little bit and tell you a little bit of the origins of CMS precision timing. And that again comes back to Caltech. This is a picture taken by me in 2013. When Maria was coming back from CERN, and we were discussing on how to set up a new lab, and we were able to find a little corner in all Minos lab, and we started to probe the properties of LYSO in terms of timing. And since there, we have evolved significantly to the facilities that are currently present at Caltech. This is how the new lab looks. And it's a state-of-the-art facility with many precision instruments, where we have trained a lot of undergrads, grad students, and we're making a lot of progress for the construction of the detector. And I want to give a special credit to, here at the bottom, you see Jason Trevor, who has been part of the HEP group and enabling all these experiments, including now ours, since 30 years, and he's also a Caltech graduate. Here you have Lautaro Narvaez, who is a junior engineer, electrical engineer, who has been doing a lot of high-speed electronics and readout systems for our timing detector. And last but not least, you here see your own Adi Bornheim, who is connected over Zoom, and he is actually leading the construction of the detector from CERN. Now, again, as I said before, we need to take these prototypes and then test them in conditions that are ideal or very similar to what we'll experience at the Large Hadron Collider. And the closest that we can achieve that is to take them and put them in beam experiments, And we have two facilities that we've used, one at Fermilab, the top picture, and one at CERN, the bottom left. And the bottom right picture is a picture of the first ever beam experiments that we've done back in 2013 again. And we have here from the left to right, we have Javier Duarte, who is a grad student at Caltech and now is assistant professor at UCSD. Then here next is me, a couple of years younger. Here is Serge, who is a Caltech research professor here at Caltech and also affiliated with Fermilab. And here we have our legendary Anatoly Rongin, who is one of the inventors of the fiber calorimeter. And we have learned a great deal of things from him. So that's how we started. And now I'm gonna go back to the main topic, which is the detectors that we're trying to build. So remember, the barrel part of the detector is composed of two technologies, one scintillating crystals, which are called LYSO. Those produce photons. The photons are read out by a different technology with a photosensor, which is called a silicon photomultiplier. And both have come a long way since about 2000 to now 2020. So it's the first time that we can put together this technology that has the radiation harness properties to withstand the LHC collisions and deliver the time resolution that we need. And in the particular case of the scintillating crystals in the left, LYSO, the groundwork was already done on the properties of the LYSO, but by Caltech, Ren-Yuan Su and Harvey Newman. And we use all these measurements to actually make the decisions and go with the technology that we have chosen. So now that we have the sensors, we need to package them together. So that involves creating custom-made precision or high-speed electronics to read out the signals in order to give you good timing. Then you need to assemble this, the silicon photomultipliers with the LYSO into one package. And particular geometry that we're using is not simple, so we need to use two readout boards and so on and so forth in order to achieve the precision that we need. And this was done for the first time to achieve these levels. And we take these sensors, and as I said, we test them at the beam facilities. So we take it, in this case, to Fermilab, where we combine our precision timing sensors that we want to test with precision position reconstruction that's available at the beam facility. And we make protons go through the sensors that will mimic the signals that we'll observe at the LHC. And then we can reconstruct their position. And more importantly for us, the timing precision that we will obtain. And here are the first results that we have obtained, in which we can clearly see the shape of our sensor being hit by the protons. That's the red part here in the picture. And that enables us to say that we're correctly coupling the DIQs available at the beam facilities with our own. So that gives us confidence on the measurements that we will do. And that's what we do next. And here in the plot on the right, we achieve for the first time, or demonstrate for the first time, the precision that's needed for the module that we're testing. About here in the black dots, we achieve a resolution of about 25 picoseconds independent of the position from where the particle passed through the sensor. So now moving on to the next, let me check the time. Moving on to the next part of the detector, which is the forward region, the end cap. As I said before, and let me try to explain this a little bit in more detail now, the logic. So the end cap region usually has more particles going through, therefore the radiation is bigger, and therefore we need a detector that can withstand that radiation for the time that we need to run the experiment. And LYSO and CPEM was not a possibility, so we need to find a new detector. We knew that silicon was a very good detector in terms of radiation hardness, but in order to overcome the noise and get the precision of 30 picoseconds, we needed to have a new sensor that had gain. And that's what happened in 2013. There was a new detector coming called the low gain Avalanche detector. And this is new. It has never been done in large quantities. As we said, we need millions of channels at the LHC, and we need to create new electronics to be able to read out this system. So this will be a major challenge and one that we're trying to tackle. So, and again, this first generation, this technology in particular has a lot of promise because it's a first generation 4D tracking technology. That means integrated in the same sensor position reconstruction and time reconstruction. And that has gained a lot of traction. Other experiments like Atlas, the other experiment at the LHC, and also experiment at the electron ion collider that's proposed, are thinking about using this technology for their detectors. and as such has been highlighted as a priority in the DOE Basic Research Needs Report. Now, coming back to the timing layer of the end cap, this is how we achieve this detector. So usually in silicon, you don't have any gain layer. And what we do in order to achieve this gain layer that will overcome the noise and give us good signal to noise to achieve good timing, you dope this sensor with other materials in order to increase the electric field in this region. And by increasing the electric field significantly, you create an avalanche. And that gives you the multiplication factor and therefore the gain. And this is pulses coming out of the LGAT sensor. And as you can see, they are very narrow in time, about 1 nanosecond. And that's very good for timing properties. And we also get the good signal to noise that we were looking for. This is actually how one of them looks like, the one on the right. And this is the first time that we were able to test these sensors in a beam in order to prove their performance, both in time or also in position. The first time ever. As I said, these were new sensors, therefore we were testing them for the first time. And this is what we commissioned in the testing facility again. And we had found that they have very good efficiency for particles that we will detect at the Large Hadron Collider. And this is the same slide. And what concerns the timing performance, which is the plot here at the bottom, you can see again that we're moving along the x-axis. And in here, we transition from one pixel of the detector to the other. And this, again, the first time that was done. And we commissioned that the time resolution is consistent to what we need, about 35 picoseconds for minimum ionizing particles. Okay, so let me pause here for a minute. I think we're changing gears. Yeah, so we're changing gears a little bit. So now we have proven at this point that the performance that we need from the sensors is achievable, and we're working towards the construction of the CMS timing detector that will be installed at the High Lumi LHC. And before I forget, all these measurements that I just showed you were critical, again, for having this project approved by the funding agency. So now we're a fully fledged project, and we're pursuing the construction, active construction here at Fermilab, which will construct the end cap timing layer, and also at Caltech, which will be one of the production centers for the barrel timing layer. And now moving forward, again, coming back to this question is that what can we achieve by having such performance from precision timing? And another interesting possibility is the realm of long-lived particles, which we briefly touched on. But in this case, it's coming back to the Higgs. So the Higgs now can be a portal to these long-lived particles. So the Higgs can couple to long-lived particles, and then the long-lived particles decay again in the detector. And up to now, we have looked for these particles in a particular topology or way of reconstructing particles in here in red. And we call that topology displaced vertex, because we have such good tracking reconstruction and very detailed and fine sensors, we can kind of precisely track from where these particles are coming from. But again, timing adds a new dimension, so we can use now the timing detector to have new capabilities for long-lived particles by just recording the time at which these particles hit the new detector. So that will be something new that we'll be able to do in the next phase of the High Lumi LHC, which will happen in 2027, to remind you the time scales. But now, because of this exposure to long-lived particles, there comes this realization of how natural are to have these long-lived particles in beyond the standard model processes or models. And one key feature of this, our own standard model that we know and we love, is that it comes with a lot of long-lived particles all together. So we have the tau, the K longs, the K shorts, the muons, the pions, the neutrons. All of those particles that we know are long-lived, and the same mechanisms by which they are long-lived in the standard model, they also appear in beyond the standard model. So beyond the standard model, particles that are long-lived are very natural for the same reasons that we observe them in the standard model. Now, as I tell you, we will be good for long-lived particles starting in 2027, which we call run 4 or the High Lumi LHC. But now we're currently taking data, and we have collected data in what we call the run 2 of our experiments. And the question that, or these are the facts, that CMS was not built with explicit LLP capabilities, but still CMS is a cutting-edge multi-detector system. And the question then that we want to pose, or I wanted to pose, is can CMS be transformed into a real LLP experiment? And the short answer to that, after doing innovative thinking and trying to understand the principles by which LLPs are detected in any detector system, the answer is yes. And that's what we've done in this new search that we're trying to perform, which we have observed this signature for the first time at the LHC. Let me walk you through it. What happens is that we produce long-lived particles here at the very center of the picture. The long-lived particle travels in this dashed line to the very end of our detection system, which is the muon chambers or the muon system, and then it decays there. And these little yellow dots are just the manifestation of a shower that occurred in the muon system, and we can reconstruct that. And the signature is a large cluster of hits coming from the shower of this particle. And we are using now the muon system that was not intended for this as a sampling calorimeter. So now by looking or thinking differently, we can be able to now have very good sensitivity for such signature. And let me try to make that point a little bit more clear, because this is what happened on CMS when you don't do this. And the way I say it is that the current CMS data analysis chain is completely broken when it comes to LLPs. We don't trigger on these particles. It means that we don't record them in some cases. The particle reconstruction algorithms that we use, they have a paradigm in which they assume that the particles are coming from the beam spot. Therefore, we will miss some of these long-lived particles because of that. And because of the huge amount of data that we collect, we also make decisions on the objects that we saved in the final state based on prompt assumptions. So a lot of these things that were decisions that we took, and rightfully so, at the beginning of the LHC, need to be revised. And that's what we've done. We've put all of that together, and we have fixed the chain. We have now identified a way to trigger on this signature. And by doing so, we're also enabling new triggers that will be dedicated for LLPs past 2022, which will start taking data again. We have redesigned the muon system reconstruction to allow for the signature that I just showed you. And we also have designed new data formats in order to be able to do the final result and the final product. And now coming to the final product, this is what we have achieved. And what happens is that the green curve was the current state of the art reach for long-lived particles in the case where the Higgs decays to two of these scalars that are long-lived. And this new result is the black curve. And as you can see, the lower you are, the better the sensitivity. The y-axis is the branching ratio of the Higgs decaying to two of these scalar particles. And now we're sensitive to about 1e-3, which is orders of magnitude better than the previous state of the art. And that was just enabled by redesigning or reimagining how the CMS reconstruction had to be done. Okay, so now coming to the second way in which I am addressing these grand challenges by being in the frontier of detection technology is using quantum sensors to probe, in particular, dark matter, and how we transition the usage of these quantum sensors from their typical use in quantum communication to fundamental physics. And this is not a new idea. This was actually presented in 2017 by Catherine Zurek here in the same colloquium series. And what she told us at the time is that we need to leave the WIM paradigm of the traditional WIM masses and explore the low mass regime of the SARO, which is the dark matter mass, in order to probe well-motivated models that are not possible with the current detectors that we have. And these ideas were also taken by the community and compiled in the US Cosmic Vision report, and we're also Sunil Golwala from Caltech. They are co-conveners of this. And what we're trying to do is follow this program and enabling in real detectors. That's what we're trying to do. So before that, let me explain you how we're transferring this from the quantum information science part, where we have studied teleportation models. So we started with that. We take these quantum sensors and we use them for quantum teleportation. And quantum teleportation, in very few words, is a disembodied transfer of information. And what does that mean? In this case, we need to send, we want to transfer the quantum state of a photon from one place to another, which are not connected geographically. And we do that, or we enable that by using the properties of quantum entanglement. That's in a few words. So that's what we do. This is the actual implementation that we have to achieve that realization. And these are two sibling systems, one at Fermilab and Caltech, and we call them the Fermilab Quantum Network and the Caltech Quantum Network. In this case, we teleport photons of a wavelength of 1536 nanometers. And I don't want to go over the details of this because the foundations of this work for teleportation have been done by Jeff Kimball 20 years ago. And I'm sure that he can explain it way better than me. But what I wanna stress here is that now we are benefit from the state-of-the-art detectors, optics, electronics, and in particular the quantum sensors to allow us to do these experiments in more control, in a control and stable way, stable manner, in order to scale this system up. And this is pictures of now how the networks or the setup looks in real life. The picture here, we have Raju Valivarti, a postdoctoral scholar at Caltech, who is setting up all the optics and the optimization for the network, and two graduate students, Andrew Mueller, who is setting up the superconducting nanowire detectors, and Sam Davis, who is monitoring the teleportation fidelities that we are achieving. So now let me flash these results very quickly. And the left one is a plot which is called the Hong-U Mandel Effect, or HOM-DIP, which tells you the degree of indistinguishability of particles, which is very important to ensure that you will succeed in your quantum teleportation. And we see a clear contrast in this plot. So that will tell you that we should be seeing quantum teleportation. And on the right, you see the final result, which is quantified on a fidelity number, which tells you how well you are teleporting these states. The closer you are to 1, the better you are doing the teleportation. And in this case, we have achieved record high fidelities for this type of systems over 44 kilometers of fiber. And this was highlighted in the first edition of PRX Quantum, and this it's the actual number of that publication. So now coming back to the dark matter side, I wanna stop a little bit on the sensors that enable to doing such searches. These are the superconducting nanowire single photon detectors again, or SNSPD for short. And I wanna tell you the key properties that make this detector a good sensor for dark matter. So they are sensitive to very low threshold, in this case, 100 millielectron volt or a 1/10 of electron volt. They have achieved very high system detection efficiency for photons, about 90%, very low dark count rates, 1e minus 4, so hertz, and state-of-the-art time resolutions of about 3 picoseconds. And how do they work? Is that you have, you cool them down, you have superconductivity, you run current through it, there's no resistance, and then radiation comes here, and it's impinged in the sensor. It creates a hotspot, or it deposits its energy, and because it's a superconductor, then this hotspot starts to grow and grow and grow until the resistance, because of the wire going not superconductive, the resistance goes up very quickly, and then all the current goes to a readout system, and that's how we get our electrical signal. And the foundational work for this and the continued R&D, it's credited to JPL and NIST, and we are collaborating very closely with them through the InQNet program that I mentioned in my very first slide. So now, how does the dark matter part work, or how do we do it? So let me explain to you how typical dark matter experiments work, or generically work. You have dark matter coming into your target. So you have a target sensor, then dark matter will interact with your target, and then it will deposit some energy. We call that the recoil energy. Then you read out this recoil energy, and that usually gives you an electrical signal. Now, the interesting thing is that because of the mass of dark matter and because we know the velocity of dark matter, then it has a fixed kinetic energy, and the kinetic energy of dark matter and the recoil, which is related to the threshold of the detector, will set the ultimate reach of your detector. So let's say for, I think that's more clear, which is the same slide with now with a different message, is that to probe low dark matter masses, you need low thresholds of detector, so you can see the signals from these light masses. And the rule of thumb is that for example, for a 1 MeV dark matter particle, you need about 1 EV of energy threshold on your detector. So that's kind of the relationship, and that relationship is fixed. So the lower you go in threshold, the better or the more you will probe the dark matter space in terms of low mass. So we know that, and we have a sensor that can achieve that. But what we realized, or what was realized recently, is one way to pursue this in order to increase the target mass is use similar to what we do at the LHC. We use a scintillator, and then we read the scintillation light with the SNSPD. So the scintillator has been recently demonstrated to scintillate in cryogenic environments. It's gallium arsenide, and it scintillates infrared photons. It's cryogenic operation, as I just said, and it has no afterglow. It means there are no photons that come after of the interaction, which is very important to fight backgrounds that will arise in dark matter experiments. And on the SNSPD side, which will be coupled and we will read out the photons, we have high efficiency for infrared photons, very low dark counts. It also has, by default, cryogenic operations, and it has superior time resolution, which we can use again to reject backgrounds that we will observe from, let's say, radioactive sources in our setup. So here is the idea. Again, it's the same idea or the same picture that I had before. So dark matter comes in and interacts now, in this case, with our target. In our target, the case will be gallium arsenide. And then what happens next is that energy that's deposited, that's here. So then the question is how much energy you deposit? Well, that, as I said, depends on the dark matter mass. This is a plot of in the x-axis of the recall energy, or the energy that is deposited in gallium arsenide, and the two lines are the different dark matter masses. So black is 1 GeV, and kind of bluish is 10 MeV, so 100 times smaller. And you can see that the black one has a longer tail, which means a harder recoil, more energy being deposited. And the lower mass, it has a softer or more sharp cutoff, because it carries less kinetic energy. But you can see that about most of the energy, it's about 6 electron volts. And if you transform that into number of scintillating photons, that's on the range of 1 of 2 photons that you emit per scintillation light. Therefore, we can use now, we can put it all together, and that's here, where you have dark matter come in, it deposits the energy on the left plot, and then the gallium arsenide scintillates. Those are the red lines, and then we read out the photons that are scintillating with the SNSPDs, and ultimately we get an electrical signal that we will read out in our system. So that's kind of the experiment idea, but that will basically bring us, if you were to do this experiment in real life and you were able to find all the backgrounds, which is the assumption in most of the reach plots that we have in dark matter, you go from a few tens of MeV to now being able to probe 1 MeV dark matter. So we're clearly going past the WIMP paradigm, and we're starting to probe ever so low masses, and we're enabling this by using these quantum sensors. And this is plot here with the red curve, which is the gallium arsenide, and all the other curves are predictions for other scintillators. So you can also do this with other scintillators, but we have picked gallium arsenide because it's been shown experimentally that you can achieve scintillation at cryogenic temperatures. And this was done at LBL, and that's what we're collaborating with. That's my next slide. So we have this new collaboration with LBL, JPL, Caltech, and Fermilab. And we are currently, or more correctly, one of our main grad students, Jamie, is performing simulations to understand or better understand the better way to read out the light, or what we call the light collection efficiency, determine what's the maximum thickness of gallium arsenide. And additionally, we are now setting out shop again for this particular experiment here at the first floor of Lauritsen, where we are going to perform laser and radioactive calibrations in order to understand this sensor, because it is very exciting because it's new. We have never done this type of experiments before. It's the first time that we want to couple an SNSPD with a gallium arsenide at these cryogenic temperatures. So we need to do this from the very scratch, and it's very exciting because it's very new. So coming back to almost the last slide, as I said before, now these particular SNSPDs, they have a threshold of about 1 electron volt. And what I told you in the beginning is that they've been proving to work for 1/10 of that. And that's shown by this red curve here. And if you have very good eyesight, the red one means a 10 micron photon, which if you convert that to energy is about 100 millielectron volts. And they've been shown to do that. And our idea is to keep pushing the threshold of the detector even so lower through continued R&D with JPL, NIST, through the InQNet collaboration, and enable future dark matter experiments that can probe lower dark matter masses. So that brings me to my outlook. And just to summarize, I'm executing the construction and residual R&D for the first ultra precision timing detector system in Hadron Collider experiments. We're extending the existing capabilities of CMS to probe new physics and the Higgs sector, implementing the ambitious quantum sensor reliant dark matter program that I just described for ultra low masses. And more importantly, this is a decade-long, very interesting research program that could present us with fundamental discoveries that again could reshape our field and give us hint on what's next and what lies ahead. So with that, I want to conclude. Thank you. And that's all I have for today.
Thank you, Cristian. I think this was a complete overview and summary of the program. So we can take some questions now, and Colby can help us monitor this.
So if anyone has a question, you should see the raise hand button on the bottom of the screen if you're on a computer.
I want to mention that Cristian is here at the labs. He's visiting from Fermilab, and so he's going to be here the next few weeks, and he will have a chance to interact with anyone over Zoom or on campus in a COVID-safe way. Of course, he's tested twice a week, as is normal for all of us who get on campus. So if there is no pressing question, let me ask a question. Can you tell us a little bit about the scale of the cost of this new detector at the LHC? And you mentioned the very dense number of channels, etc. What is the cost of this detector? Just for people to know.
You're talking about the timing detector, right?
Yes, about the timing detector, yes.
Yeah, so it's a great question. So we have now been approved via a full project, and we're going to construct this detector. So in the cost, it's about 20 million. And it's kind of divided evenly between the barrel and the end cap. So 10 or 11 millions each, give it a take.
And so given the scale of all the detectors of the LHC is a piece of cake, nothing.
Yeah, it's small compared to that, yes.
Good. Anybody else has any questions? If not, let's thank Cristian, and anyone who wants to contact him, he will be around in the same time zone with us for the next 2 weeks. So thank you, Cristian, very much.
Thank you. Bye.